You think you know what cold feels like. You have stood in winter air and felt it pull the heat from your face. You have held ice and felt the sting work its way through your fingers. You have been cold enough to shiver, cold enough to lose feeling, cold enough to understand in your body what the word means. None of that has anything to do with what space actually is. The coldest temperature ever recorded on the surface of Earth was -89.2 degrees Celsius. Vostok Station, Antarctica, July 1983. A temperature so extreme that exposed skin freezes in under a minute. That a breath of that air damages lung tissue. That metal becomes brittle enough to shatter like glass. The average temperature of space is -270.45 degrees Celsius. That is not a larger version of Antarctica. It is not cold in the way that Antarctica is cold, extended further along the same scale. It is a different category of physical reality. A condition so far outside the range of anything living tissue has ever encountered that the word cold is almost the wrong word for it. And the way it would kill you is not what you think. Start with the number. Because the number requires explanation before anything else makes sense. -270.45 degrees Celsius. Also written as 2.7 Kelvin. The Kelvin scale measures temperature from absolute zero, the theoretical point at which all molecular motion stops completely, at which matter contains no thermal energy whatsoever. Absolute zero is -273.15 degrees Celsius. Space sits 2.7 degrees above absolute zero. Not 27 degrees. Not 270 degrees. 2.7 degrees. The gap between the coldest possible state of matter in the universe and the average temperature of the void between the stars is smaller than the temperature difference between a warm room and a cold room on Earth. That number, 2.7 Kelvin, is not arbitrary. It is not simply the absence of heat, the result of there being nothing in space to warm it up. It is a relic, a fossil of the earliest moment in cosmic history. The universe began approximately 13.8 billion years ago in a state of unimaginable heat and density. As it expanded, it cooled. The light from that initial fireball stretched as space stretched, its wavelengths growing longer, its energy diminishing. What was once a blinding radiation field filling all of space is now a faint microwave hiss permeating everything, everywhere, detectable in every direction you point a sensitive enough instrument. It is called the cosmic microwave background. And it is what gives space its temperature. The 2.7 Kelvin of interstellar space is the temperature of the afterglow of creation. The cooled remnant of the Big Bang, stretched across 13.8 billion years of expansion, still present, still measurable, still the baseline thermal reality of the universe. You are not cold in space because there is nothing there to warm you. You are cold because the universe itself is 2.7 degrees above the coldest possible state of matter, and the only reason Earth is not that temperature is because we orbit a star. Now, what it would actually do to your body. This is where the science diverges sharply from the movies. From every depiction of space exposure that popular culture has produced. The frozen astronaut. The body turning to ice in seconds. The dramatic, immediate crystallization of flesh. That is not what happens. The mechanism of heat transfer that makes cold dangerous on Earth is conduction. Direct contact between your body and a colder material. When you hold ice, heat moves from your hand into the ice because heat always moves from warmer to colder when two objects are in contact. When you stand in cold air, heat moves from your skin into the air molecules colliding with it. The denser the medium, the faster the conduction. Ice conducts heat away from your body faster than air, which is why falling into freezing water is far more dangerous than standing in freezing air at the same temperature. Space contains almost nothing. In interstellar space, the particle density is approximately 1 atom per cubic centimeter. In the near-Earth space environment, it is somewhat higher, but still effectively a vacuum by any practical measure. There is almost no medium for conduction. Almost nothing to touch your body and pull heat away from it. This is the first thing that makes space cold in a way that defies ordinary intuition. The extreme cold of space cannot kill you the way ordinary cold kills you. Because the mechanism of cold killing, conductive heat loss, barely operates in a vacuum. What operates instead is radiation. Every object above absolute zero emits thermal radiation. Your body, right now, is radiating heat into the environment around you. In a room at normal temperature, you are absorbing roughly as much heat from the environment as you are emitting, and the balance feels comfortable. In cold air, you are emitting more than you absorb, and you feel cold. In space, you are emitting heat continuously into a 2.7 Kelvin environment, and the return radiation from that environment is essentially zero. You would lose heat. Slowly. Far more slowly than the movies suggest. A human body in the vacuum of space would take somewhere between 12 and 26 hours to cool to the ambient temperature of space through radiation alone, depending on orientation, surface area, and the presence of sunlight. Sunlight complicates everything. If you were exposed to space in direct sunlight, in Earth orbit, for example, facing the sun, the radiation pressure from our star at that distance delivers approximately 1,400 watts per square meter to any surface it strikes. Your spacesuit in direct sunlight reaches temperatures approaching 120 degrees Celsius on the sun-facing side. The shadow side of the same suit simultaneously drops toward minus 160 degrees Celsius. The thermal engineering challenge of a spacesuit is not keeping an astronaut warm in the cold of space. It is managing the simultaneous extremes of intense solar heating on one side and near absolute zero radiative cooling on the other. The suit has to move heat actively, continuously, from the warm side to the cold side to maintain a livable temperature inside. When that engineering works, an astronaut survives. When it fails, the margin between life and death is measured not in hours but in minutes. But remove the suit entirely. Remove the engineering. Place a human body in the vacuum of space in direct sunlight. The cold would not be the first thing that killed you. The vacuum would. Your lungs would experience the pressure differential first. At sea level on Earth, the atmospheric pressure pushing on the surface of your body is approximately 101,000 pascals. In space, the external pressure is essentially zero. The air in your lungs, at the moment of exposure, is at normal body pressure. With nothing pushing back from outside, that pressure differential would cause the lungs to expand rapidly. If you had exhaled immediately before exposure, if your lungs were empty, you would survive the pressure change with no permanent damage. The human body is flexible enough to handle the sudden absence of external pressure without rupturing, as long as there is no air pressure inside pushing outward. If you had inhaled, if your lungs were full, the expansion of that trapped air would rupture the alveoli, the tiny air sacs where gas exchange happens in breathing. They would tear. You would experience a pneumothorax, a collapsed lung, almost instantaneously. Simultaneously, the dissolved gases in your blood and tissues would begin to come out of solution. The same process that causes decompression sickness in divers who ascend too quickly. Nitrogen bubbles forming in the bloodstream, in joint tissue, in the brain. The bends, as divers know it, but compressed into seconds rather than minutes. Your saliva would boil. Not from heat but from the absence of pressure. At low enough pressure, water boils at body temperature. The moisture on the surface of your eyes and in your mouth would begin to vaporize. Your tongue would feel it first. A wet fizzing sensation as the moisture on its surface turns to gas. Your skin would not explode. This is a persistent movie myth. Skin is strong enough to contain the pressure differential. You would swell. Your body would expand slightly as gas and fluid redistributed. But you would not rupture. You would lose consciousness in approximately 10 to 15 seconds. Not from the cold. Not from the vacuum directly. From hypoxia. The same oxygen deprivation that causes blackout in free divers, in pilots pulling high G-forces, in anyone whose brain is suddenly deprived of oxygenated blood. At the moment of vacuum exposure, the partial pressure of oxygen in your blood drops to zero. There is no atmospheric pressure maintaining the gradient that drives oxygen from your lungs into your bloodstream. The exchange stops. Your brain, the most oxygen-dependent organ in your body, begins failing within seconds. Unconscious in 10 to 15 seconds. Brain death beginning within 3 to 4 minutes if oxygenation is not restored. Here is where the medicine becomes strange. If you were rescued within those first 90 seconds, if pressure was restored before permanent damage had occurred, you would likely survive with no lasting injury. The human body is remarkably resilient to brief vacuum exposure. We know this not from theory but from accidents. In 1966, during a ground test at NASA, technician Jim LeBlanc was accidentally exposed to near vacuum conditions when his spacesuit pressurization hose disconnected. The chamber pressure dropped to less than 1 pascals in seconds. He reported feeling the saliva on his tongue begin to boil before losing consciousness. He was rescued in roughly 30 seconds. He survived completely unharmed. His description of the boiling saliva is the only first-person account of vacuum exposure in the scientific literature. But here is what medicine cannot fully explain. At 2.7 Kelvin, if your body was somehow exposed to the true ambient temperature of deep space, not in low Earth orbit with solar radiation present, but in the interstellar void, away from any star, at the baseline temperature of the universe, the process of death would be so slow and so physiologically unprecedented that medical science has no complete model for it. The conductive heat loss is negligible. You are losing heat only through radiation. Your core temperature would drop at a rate of perhaps 1 degree per hour initially, slowing as the temperature differential between your body and the environment decreases. Your cardiovascular system would begin failing as core temperature dropped below 28 degrees Celsius. The heart enters ventricular fibrillation, a chaotic, ineffective quivering rather than coordinated pumping. At 20 degrees Celsius core temperature, the heart typically stops entirely. But here is the strange part. In profound hypothermia, the brain's metabolic demands drop dramatically as temperature falls. There are documented cases of people surviving core temperatures as low as 13.7 degrees Celsius, a temperature at which cardiac arrest has been present for hours after being rewarmed. The record for survival from the deepest hypothermia ever recorded belongs to a Norwegian woman whose heart stopped for over 3 hours at a core temperature of 13.7 degrees Celsius. She survived neurologically intact. The cold that kills you in space would kill you with a slowness that creates a physiological paradox. Your body would enter a state of extreme metabolic suppression. Heart stopped, brain activity essentially ceased, all cellular processes nearly halted, that in other contexts we have learned to recognize as survivable with the right intervention. There would be no intervention. You would be in a state that medicine classifies as potentially reversible, in a location where reversal is impossible. The body saying, biologically, not dead yet. The physics of the situation saying, there is nothing that can reach you. That is the specific cruelty of the cold of space that medicine cannot fully account for. Not that it kills quickly. Not that it kills dramatically, but that it kills at a pace and through mechanisms that sit at the boundary of what we classify as death and what we classify as something else. Something that is not alive. Not dead. Simply cooling. Toward 2.7 Kelvin. Toward the temperature of the universe itself. Toward the cooled remnant of the light that filled everything when time was young. NASA physicists studying the thermal environment of deep space are not doing so to describe how astronauts die. They are doing so because thermal management is one of the most technically demanding problems in space engineering. Every spacecraft, every instrument, every electronic component has a temperature range within which it functions. Too hot, the electronics fail. Too cold, lubricants freeze, materials become brittle, battery chemistry stops working. Voyager 1, at 24 billion kilometers from Earth, is operating in an environment where the ambient temperature is 2.7 Kelvin. Its instruments are kept functional by heaters powered by the same RTGs that drive the spacecraft. As those RTGs decline in power output, the heaters are being selectively shut off. Systems are being allowed to cool toward the ambient temperature of interstellar space as the power budget shrinks. The spacecraft is doing, in slow motion and by degrees, what a human body would do in that environment. Cooling. Not from conduction. Not from wind or contact or the pull of ice through skin. From radiation. The slow emission of thermal energy into a universe that is 2.7 degrees above the coldest possible state of matter, and that takes everything you give it without giving anything back. The Webb telescope manages a different version of the same problem. Its primary mirror and instruments must be maintained at approximately 40 Kelvin, minus 233 degrees Celsius, to detect the faint infrared signals from the earliest galaxies. The telescope sits at the L2 Lagrange point, shielded from the sun by a 5-layer sunshield the size of a tennis court. On the sun-facing side, temperatures reach 85 degrees Celsius. On the telescope side, the shielding reduces the solar input enough that the instruments can cool passively to their operating temperature. The thermal engineering of Webb is, in a sense, the engineering of controlled exposure to the cold of space. Using the 2.7 Kelvin environment not as a threat to be managed but as a resource. A cooling bath for instruments that need to be colder than anything achievable on Earth's surface without massive refrigeration infrastructure. The cold that would kill you is the same cold that makes the universe's most powerful telescope work. The universe is 2.7 Kelvin. That is not a local condition. not a regional weather pattern, not a property of one part of space that you might travel around. It is the baseline thermal state of everything that exists beyond the warming influence of a star. It is the temperature of the vast majority of the volume of the universe, the enormous cold dark between the islands of light. Earth is an anomaly, a warm rock orbiting a fusion reactor, shielded by a magnetic field, wrapped in an insulating atmosphere, maintaining conditions so far above the universal baseline that liquid water, and the chemistry of life that depends on it, is possible on its surface. Step off this rock without the engineering that replicates its conditions around your body, and the universe will take the heat from you. Not violently, not dramatically. With the patience of something that has been 2.7 Kelvin for 13.8 billion years and will remain so for billions more. It will not notice you. It will not respond to you. It will simply receive the heat you emit into it, as it receives the heat from every object in the void, until the temperature differential between you and everything around you reaches zero. Until you are the same temperature as the afterglow of creation. Until you are as cold as the universe has always been. That is not a horror story. It is a physics equation. And the answer it produces, every time, is the same. Thanks for watching. I'll see you in the next one.